All right, welcome back from a very, very short break. My name's Scott Collis again from Argonne National Laboratory. We have next speaker is Thomas Chen, who is going to be talking about deep learning with Python for natural disaster relief from satellite imagery. So Thomas, if you could share your presentation and we'll get going.
All right, thank you so much, Scott. And before I get started, there is a poll. Just wanted to know from the audience whether you're familiar with PyTorch, the library that we primarily used for this project, just as a basis for what I'm going to be presenting. So I'll just give folks a little bit of time to fill that out, and then we'll get started. Give it maybe 10 more seconds. All right, perfect. So looks like most people have heard of it and maybe have used it a few times. A couple people have used it extensively, and there's a sizable number of people that are not familiar with it at all, and that's totally fine. So anyway, let's get started with the presentation.
That looks
all right, perfect. So today we're going to be talking about using deep learning with Python with the PyTorch library, specifically for natural disaster relief from satellite imagery. So obviously this is a really important issue that comes up because due to climate change, there is an increased frequency and intensity of extreme weather events. So whether that be hurricanes, forest fires, tornadoes, due to climate change, these are increasing in frequency and severity, and therefore it is really important to have automated mechanisms in place to be able to assess the damage caused and to develop pipelines for relief in a timely manner for the allocation of resources and personnel to minimize the number of lives lost and the economic value lost. And we're going to focus really on building damage assessment after natural disasters because that is really a parameter that we can utilize for assessing how much damage was caused. While that's not a perfect measure because, there could be damage outside of buildings, people might have been affected, not necessarily in buildings, but because it's a good parameter and they're visible in imagery, satellite imagery specifically, they're a good parameter, and we use that data to train our deep learning models. So again, the background is that even, whether it's due to climate change or not, whether, we can talk about earthquakes as well, seismic events, these are really devastating and cause countless lives lost and economic value lost as well. And, because artificial intelligence has become almost ubiquitous in recent years, there have been a number of models developed to try to both predict and assess, so pre and post disaster, to deal with climate mitigation and adaptation. But specifically with assessment, there are a number of ways that we can do that. And this is a pressing issue. And while algorithms have been developed, deployment is not widespread at the moment, and so that's also an important aspect to consider. So we talk about satellite imagery as a source of data because it's efficient to obtain in real time, especially when we want to deploy this technology, and would aid in the allocation of resources to affected areas. And we're going to analyze it with deep learning-based approaches, as I previously mentioned. Previous works in this area, let's start really broad with image classification. Of course, computer vision, the study of computers gaining high-level insights from imagery and video. And so, before around 2012, that was when classical approaches were the standard. And then in the past decade, we've seen deep learning techniques, neural networks, such as convolutional neural networks, really gaining ground and really being the standard for what we do in deep learning and image processing. So computer vision for satellite imagery, though, specifically has yielded a number of really interesting results, from marine ecology to weather forecasting, to forecasting and assessing the spread of diseases, so like pandemics, agriculture, assessing that, urban road damage or urban development as a whole. And then also in all of these cases, we can use change detection, which is a form of multitemporal fusion where we detect, for example, with these natural disasters, if we have a pre-disaster image and a post-disaster image taken in the same location, we can train a neural network essentially on the change that has occurred between those two instances in a multitemporal fashion. And that is useful not only with natural disasters, but like I said, with agriculture, across seasons, across years. Urban road damage, urban development, to see how an urban area has expanded and things like this. And then more specifically on building damage assessment, which is what we focus on, we have semantic building segmentation, like we see on the right, where we see, this is actually from the same data set that we're going to use, but we have a pre-disaster image and a post-disaster image there. So you could see there is not really much damage on the left, and then some damage on the right. It's a little bit hard to see. It's a little bit small in this case, but we can see that on the bottom, we see semantically segmented buildings, with green representing the buildings that were eventually not destroyed, and then red destroyed. And this is just a binary classification, which is obviously not a perfect mechanism, but it's just an example. We also have cross-region transfer learning. Because, and it can be difficult because in different geographical locations, we have different building, the way buildings look can be different. We can have small huts in some places. We can have skyscrapers in others. So that's something to consider. Semi-supervised approaches as well. But in this work, I'm going to be presenting a supervised approach with labeled data. But finally, we have XBD, which is the most comprehensive data set developed by the XView2. In collaboration with the Geospatial Intelligence Agency. And that is the most comprehensive data set because it includes pre-disaster and post-disaster imaging on a variety of different disasters and in a variety of geographical locations. And it's especially good for conducting this kind of research or these kinds of projects where we want to assess what damage has been caused by disasters. Now, when we talk about the data that we train our machine learning models or deep learning models on, there are a number, like I said, satellite imagery is one, but social media is also another form of data, that can be, many people are surprised by how that can be useful. There are a number of ways we can use it. We can use it in a natural language processing setting or computer vision setting. In a natural language processing setting, we would mostly be thinking about sentiment analysis. And, because social media is such a ubiquitous technology that people utilize for communicating during extreme events or disasters to both their family and to just the entire world as a whole, sentiment analysis on what is going on during the disaster, pre, during, and post the disaster, as well as computer vision. Of course, this is similar to satellite imagery, but it's on the ground data. Social media has emerged as a way to really crowdsource that imagery. And, it can be used for building damage assessment as well as, other types of assessment of what has happened during the disaster. So both those instances, both the imagery and the text and social media can be used. But what do we contribute? In this work, we also focus on interpretability, not only working off of this comprehensive data set, the XBD, and working towards state-of-the-art results, but also trying to facilitate interpretability. So qualitative and quantitative, in a qualitative and quantitative manner. And interpretability, for those that are not familiar, is the degree to which a human can understand the cause of a decision of a machine learning algorithm. Many times with deep learning models and neural networks especially, we end up with black box models where we really just aren't taking into account, domain specific knowledge, or where we just don't know why the prediction was made, and it's just garbage in, garbage out, as many people say. So it's really important that we understand, which nodes of the neural network, which layers are contributing to which parts of the decision, visualizing input weights, which modalities of the input are important for the particular prediction, maybe which input modalities are not necessary, they don't even contribute to the prediction. But it's crucial for humans to understand the cause of a machine learning algorithm and not to simply just trust the garbage in, garbage out process, because we want to be able to understand the value of the results. Not only that, but also for the overall community to trust implementing these artificial intelligence algorithms in our daily lives. If we talk about, autonomous vehicles, for example, self-driving cars, we don't want to have models that we don't know what's going on and we don't know whether the decisions that are being made are ethical. And so it's incredibly important that there is interpretability in our models, and that the same goes for the end users and end operators of our models for disaster relief. So the research process that we took was first a data set analysis, which we'll get into briefly, developing a baseline model to classify building damage based on the post-disaster image only. And that's tricky because when we don't have change detection, like I previously mentioned, involved, that's a little bit difficult because we're only looking at the result after the disaster and not what happened before. We can develop improvements in the baseline model to classify building damage based on other aspects of the image, so pre-disaster image and the disaster type, as well as comparing all the results and then understanding what these networks are learning, what inputs are important, also developing qualitative saliency maps to understand which parts of the image that it's looking at, all of the above leading to more interpretable models. And hopefully for real deployment. So the XVD dataset, like I previously mentioned, it's located at xview2.org. It's a comprehensive dataset where there's a joint damage scale. Again, it's not perfect, but it is a non-binary scale. So we have no damage, minor damage, major damage, and destroyed with the visual descriptions as you see there. And importantly, we have a pre-disaster and a post-disaster pairs of images in that we can use change detection and train on that change to really understand what has happened. And so it includes from many geographic locations, from Asia to Australia to North America to South America. Previous data sets didn't necessarily have this. They mostly focused on one location, or they only did focused on one type of disaster, such as floods, floods, or just fires or something like that. But in this case, we have 5 different types. And the reason we do is because we want to be able to deploy this in a wide range of situations. And further, that it's important to see, like, is this possible? Is it possible to generalize? Is it possible to generalize over different types of buildings and different types of disasters? First, we pre-process the data, which is incredibly important, by creating building crops for per building analysis. In this case, we didn't do semantic segmentation like I showed you earlier with the, where you saw the green buildings, the red buildings. Instead, we actually did a per building analysis because this satellite imagery is pretty high resolution. That is possible. And so we label the building we were provided with building polygons as the ground truths, as segmentation masks. And instead of doing that, we just take a building crop, so a bounding box using the highest Y value, lowest Y value, lowest X value, highest X value, and really zoom in on that. And then we also have to discard smaller unclear buildings, such as, you see below where we have a 64 pixel building. That really doesn't help the model, and it can actually taint the training process and taint the results. So we wanted to discard some of those. And then we also wanted to use some other cleaning mechanisms to make sure that there aren't just the basic cleaning mechanisms that we go through whenever we train neural networks. And so you can see, building crop pixel area, a graph there. And then we also want to train on an equally distributed data set, so an equal number of crops per category. Obviously, this isn't always necessary, because if we use, for example, weighted F1 scores for a metric, that's not necessarily something that you need to do. But in this case, we wanted to just show, use the simple accuracy as our metric for validation and testing. And so that's what we did in this case. The baseline model, we trained, like I said, on only the post-disaster image only. We used a ResNet 18 convolutional neural network architecture. Again, convolutional neural network is the architecture that we used in ResNet 18. We pre-trained it on, well, the model was pre-trained on ImageNet data as it is often done. We use cross-entropy loss as our criterion for optimization, training on 12,800 building crops using the Atom optimizer, a learning rate of 0.001. We trained for 100 epochs, and we used NVIDIA Tesla KAD GPUs, which are really just accessible on Google Collaboratory, which is a platform provided by Google where you can use a GPU for free for 24 hours. It's useful because you need a GPU for this training, or otherwise it'll take way too long. So again, we use this ResNet 18 architecture. The specifics are there, where we have a fully connected layer, and on all the other layers right there. And then we use the cross-entropy loss function, which you see the formula for that right there. So the improvements that we made, and to assess really what parts of the input modality are important, as well as which loss functions are useful. So this contributes to that study of interpretability in a more quantitative manner. We use different types of inputs, for example, incorporating the pre-disaster image in combination with the post-disaster image, facilitating change detection. We basically concatenated the pre-disaster image and post-disaster image across the RGB channels. And then we also use disaster type because there were, I believe there were 5 disaster types. We used a one-hot encoded that into a later layer in the convolutional neural network to try to incorporate that as an input modality to see if that was an important piece of data that we needed. Different loss functions that we used also are ordinal cross-entropy loss and mean squared error. So ordinal cross-entropy loss is the same as cross-entropy loss, except it's on an ordinal scale. Which means, like, instead of classifying between cat, dog, and fish in computer vision, this time we're doing no damage, minor damage, major damage, and destroyed. It's on a scale from 0 to 3, like we saw earlier. And so ordinal cross-entropy loss also penalizes for the distance between the ground truth and the prediction. So for example, if the reality is that the damage caused to a particular crop or a particular building that we zoomed in on, if the ground truth was destroyed, but for some reason our model predicted no damage, that's obviously much worse than the ground truth being destroyed and us predicting major damage, because there's a smaller distance in that case. So that's really a useful way to do this, and we see the results of how that improved our model in a second. Mean squared error is not necessarily a really good loss function for this purpose, but we just included it to see how well that would perform in general. And other aspects remain the same for this particular experiment that we're highlighting in this talk. So the accuracy comparison, we see that if we move right, we see ordinal cross-entropy loss was the most effective, achieving a 74.6 accuracy at the most. And then mean squared error was the worst, but also incorporating more types of data. I mean, especially including both the pre-disaster and post-disaster image, as opposed to just the post-disaster image, was incredibly useful because we do have that change detection aspect in place now. But in addition, adding the disaster type was useful, especially in terms of for ordinal cross-entropy loss and cross-entropy loss. It improved the accuracy because adding that one extra piece of data probably allowed that model to gain a better understanding. However, we didn't undergo a more detailed analysis of different nodes and layers and understanding the specifics there. And that's incredibly important when doing more in-depth studies of interpretability, which is an area of future work. But in terms of the reason why it wasn't necessarily optimal in terms of the accuracy numbers, 74.6% is certainly not enough for deployment. It's because that with this non-binary classification system, where we had no damage, minor damage, major damage, and destroyed, it's often difficult for the algorithm to discern the differences between minor damage and major damage, especially more so than the other categories, because there is a lot of subjectivity in that. So even if a human were to look at and these were crowdsourced, by the way, the labels were crowdsourced. So if a human was to look at an image from this data set, or not an image, but like a zoomed in, like we did, a cropped building, and looked at the pre-disaster image and post-disaster image, and was asked, is this minor damage or major damage? it would often be difficult to actually discern that. And the same thing goes for AI. When a human has difficulty, then it's probably also difficult for an AI in terms of differentiating between categories. And that means that it is incredibly important that in the future we have mechanisms for developing classification systems that are more, discernible. But when we crowdsource, we also have to be careful about do people have different levels of subjectivity in terms of what they think that should be labeled? So these are areas of future research and future improvement. But we do see that ordinal cross entropy loss is a good loss function for a non-binary classification system, but also categories that increase in magnitude, I guess you could say, from, in this case, from 0 to 3. And then also the fact that when we add more types of data or input modalities, then the accuracy increases, but also contributing to the study of interpretability in deep learning models that classify building damage is what we essentially did in this work, but that requires a lot of future research, like I said, looking into which nodes and layers. Another aspect of it, though, is qualitative interpretability. So developing saliency maps, or in this case, specifically gradient-weighted class activation maps, or GradCam. It's depicting which parts of the building crop specifically lead the baseline model to predict a certain classification. So we have 4 images here of only the post-disaster data. So in this case, we're only using the baseline model that we developed, but we're seeing a no damage from left to right, no damage, minor damage, major damage, and destroyed. And then obviously the heat maps show, like, we're in the red areas, that's areas that indicated or led the model to believe that the prediction would be a no damage or whatever. And so it's interesting. And it's definitely something that we want to work on, not only in machine learning model applications here, but in other areas as well, in Earth observation, specifically with satellite imagery. But also expanding this gradient-weighted class activation map applications to the other models that we developed. So we're trying to incorporate that into the concatenated versions of pre-disaster and post-disaster, and understanding that a little bit further. And so the conclusion is we find that inputting different combinations of information does indeed improve model performance. And our study leads the way for more effective and efficient damage assessment in the event of a disaster. Again, the timely allocation of resources and personnel, which is so important to saving lives that are, time sensitive, is the reason why this is important. With climate change, it's only getting worse, and artificial intelligence and machine learning, these recent developments are really important in doing that. But first let's talk about future work. Other modalities of input we can also include the ground truth classifications of neighboring buildings. So, for example, if we're trying to classify a particular building, we can also use the classifications of the neighboring buildings to have some extra information that the model can work off of. Also, different combination methods for the pre-disaster image and the post-disaster image. So in this case, we just concatenated over the RGB channels. There are other methods for doing this, such as training 2 separate convolutional neural networks and then combining that information into one prediction, for example. And you could see pretty much a diagram down there on the bottom right. Qualitative interpretability, in deployment, we already talked about that. But also having a cleaner data set, so more distinct differences between major damage and minor damage, for example. There are many data sets being developed, not only on satellite imagery, but like I said, on social media data, on web scraped data from the internet, crowdsourcing this data. We have the incidence data set is one example that's being developed on the bottom left. But in any case, these are all important areas of future work that are currently going on and working towards, widespread deployment so that we can save lives. And even in, non-natural disasters, we saw recently there was a building collapse in Florida. Although that was just one building, there's potential for satellite imagery applications or social media or any type of imagery to be used, and neural networks to be, use transfer learning as well to assess what's happening and how to allocate resources and personnel to save lives. And we also saw last year with something that happened in Lebanon, where it was really devastating. In all these cases, there's a lot of future work going on. But just briefly, with PyTorch, how we did this. And I know that some people aren't as familiar with this, but there's really good resources on the PyTorch website where they provide tutorials where essentially there are resources that you can use to define a convolutional neural network, define a loss function optimizer, and train the network, and it can be applied to any kind of data that you're working on, whether that's satellite imagery like we did in this case, or whether that's just classifying different types of dogs or whatever you want. So there's a lot of resources there. I'm not going to go over it too much in detail, but this is really what I built off of and what I would recommend for any of you wishing to do some of this work on your own and work off the data set that I provided, the XBD data set, or doing any kind of computer vision projects on your own. Again, defining the convolutional neural network, loss function optimizer, training the network, and then validating it and testing it, and then really moving forward on these many goals. So it looks like that's about time. Thanks for listening, and I'd be happy to answer any questions that you may have.
Thank you very much, Thomas. First of all, I want to make an observation. I do not know how the rest of the academic community cannot keep to time, given just how amazing SciPy attendees are and absolutely nailing almost down to the millisecond time. Second of all, I want to put a quick plug out before we jump into questions. For those who are interested in volunteering for SciPy 2020, where thankfully the barbecue will be a lot better than here in Chicago. There is a Birds of a Feather at 4:10 on Gather Town. I encourage everyone who wants to help out, and almost any help will always be welcome with open arms to attend that. But now let's jump into the questions. And the first one I've got is from Kirsten, who said, sorry if I missed it, but how do you make these calculations if you don't have an image from beforehand of the disaster to compare? So can you just elaborate on the data set you used for the training?
Right. So as I understood it, the question was whether how do we train a model if we don't have the data beforehand? So in this case, we actually do have that data. The way we performed this analysis was we first started with a baseline model where we didn't have that data, where we only had the imagery post-disaster, right? So in that case, obviously the results are not going to be good, and we saw that in our results. But it's still possible to train a model because there are characteristics of damage that was caused. So even if, obviously it's possible that a building was damaged before the disaster anyway, and after the disaster was still damaged, there are cases where we can say, there was chipped paint, or the model can see this, and we can see that in the qualitative interpretability that we demonstrated. There's a roof that is, peeled off or whatever. That is evidence of it, and that can contribute to the decision. But further, when we incorporated the pre-disaster and post-disaster image for change detection over the multi-temporal scale, that improved the accuracy metrics. And so that was definitely a useful source of input modality as well.
Thank you. I'm going to use Chair's prerogative to pick the next question, even though it's out of order, but I'm really interested in the answer myself. So Shubham says, apologies if I've missed. Was the model trained on RGB channels? There are studies showing that near-infrared channels can also be used for better results. So I'll kind of expand that and say, does XBD have multispectral imagery in there? And do you think that using other non-visible channels will actually improve the skill of the model?
Yeah, absolutely. And I am aware of that research that has shown that definitely, infrared data can be useful. Unfortunately, I don't believe that this particular data set, the XBD data set, has that. And this model was indeed trained on RGB channels. But that is a very fascinating area of future research, and I'm looking forward to looking into that further.
Fantastic. Jelena asks, I'm not sure if it was said already, but are there other works in this domain? Is the 70% accuracy you show, is that considered state-of-the-art? How good is 70%?
So that is not necessarily state-of-the-art. The focus of this work was actually to demonstrate how we improved accuracy between adding different input modalities and differentiating between different criteria for optimization, in other words, the loss functions. While I do believe, because the way that we trained this was a little bit more basic than other mechanisms. We just trained a regular convolutional neural network, and the way we concatenated the data was we only concatenated it over the RGB channels instead of, for example, like I discussed, training two different neural networks for pre and post. So this is not the best results out there, and there are many results being developed at the moment. But the focus was to try to work on interpretability and potential deployment. So.
Fantastic. And last question for this session and for this symposium goes to Ed. Does the training data set have a variety of ground conditions to show in your model? For instance, snow on the ground, autumn colors, water glint or something like that. Would you expect that to be important for a model deployed to production?
Certainly having more data about that would be important. But like I said, this data was crowdsourced, and not the data itself, but the labels were crowdsourced, and so many of the labels might not be necessarily accurate, and there is not all that much information other than having a building polygon to outline where the building is located for a semantic segmentation ground truth, as well as obviously the category of disaster and the severity that was caused in terms of the ground truth. So that's more data that can absolutely be useful for training models and should be incorporated in the future.
Fantastic. Thomas, if you're on the Slack workspace, I'll encourage you to pop in there and throw up any resources you have of folks to continue the conversation in there. But we now have 5 minutes for any natural breaks you may have before the lightning talk session. So thank you to all our speakers. Thank you to my co-chair, Kirsten, and thank you so much to all the organizers and reviewers for SciPy 2021. And I keep my fingers crossed that I hope to catch up with all of you in person in Austin next year. So stay safe, everyone, and see you all soon. And that's the end of the session.